Hello, everyone, and welcome to session B4, the International Floodplain Management session. And we're going to be looking at the Kakhovka Dam attack in Ukraine and use that as a case study in disaster risk reduction. I'm Gavin Lewis, and I'm the head of engineering at Fathom, and I'm really delighted to be joined today by Barney Austin, the CEO of Aack Strategies, who are a boutique flood modeling consultancy based in Austin, Texas. Fathom and Aack Strategies have been working very closely together to deliver the current and future flood maps for the whole of Texas for the Texas Water Development Board. And I'll be presenting on this project with Reem Zoon of the Texas Water Development Board in session H8 on the Thursday of the conference. So please do come along if you'd like to find out more about the work that we're doing in Texas. So without more ado, let's talk a little bit about Fathom and give you a brief introduction to who we are. We're founded out of the University of Bristol and co-founded by two scientists doing their PhD in flood research. They set up the company really to provide and develop a global understanding of what we call water risk intelligence, essentially flood risk at a global scale, particularly in data poor areas. And we've done that, and we've provided our data to a whole range of different applications globally. One of the key things that underpins the business is research, and we have a very robust scientific background. And as part of that, we are very keen to publish our methodologies and validations in the leading peer-reviewed leading scientific journals. All our papers are peer-reviewed. We make them available on our website, and I would encourage you, if you'd like to find out more about who we are and what we do and the methods we use to develop our flood models and the science behind it, and importantly, the validation of our models, then please go to our website and use some of these papers. So what do we actually produce? We produce a range of different data sets. And of course, before you get to floods, you need to understand the terrain. Water runs downhill. We need to know that at a country scale, at a continental scale, and a global scale. And until recently, the data sets at a global scale were pretty poor. However, we've developed our own global terrain data set to underpin our global flood modeling data set. And we make that available for a whole range of engineering applications that require terrain anywhere across the globe at 30 meters. In locations like the US, where there's a lot of open source LiDAR data, we've built that into our model, cleaned that up, and we can provide that at a higher resolution, 10-meter resolution, rather than the 30-meter global terrain resolution. So now we've got the terrain data sets, one of the key components of underpinning any flood model. We have developed global flood maps. These are flood hazard maps looking at the extents and depths of flooding for fluvial coastal flooding, for the current and future climate scenarios at a global scale at 30 meters. We have those similar data sets, higher resolution, more detail for the whole of the US, including Alaska, Hawaii, and Puerto Rico, and also the UK and Japan. So that's the flood hazard data sets. We have then taken those and developed a whole series of risk scores where we can provide very rapidly analysis on portfolios of locations of assets, either in country or globally. And then for the work we do in the insurance market, we have developed catastrophe or loss models where portfolios of assets can be run against our data and calculations of dollar values of loss can be derived. That data can be available through our API, through our portal, or through our partners. So to develop any flood model, there are some key building blocks, and most of which I'm sure will be common to the work that you may do. First of all, I talked about terrain data. Now, we always try and strive to get the best data available, and that's LiDAR data. If we don't have LiDAR data, we fill in the gaps with our global terrain data, which is Fathom. So once we've got that, where we've identified the river channels and the slopes, we need obviously to put some water in that model. So we pull those inflow hydrographs from a variety of sources, essentially river gauges, particularly in engaged areas like the US and the UK. But once we've got the water in the channel, we also need to understand the channel bathymetry. So again, we try and pull that from a variety of sources. But we've also developed automated channel modeling methodologies where we don't have that information, particularly in data poor areas. So we take those building blocks and we use a hydraulic engine to really represent the physical flow, 2D flow of water across the Earth's surface. Now, I'm sure a lot of you listening today will probably use HECRAS. We use a model called ListFlood, very similar. We've done some validation of our ListFlood outputs compared to HECRAS, and there's very good correlation between the two models. So that's the key inputs. However, as many of you probably know, flood modeling is not straightforward and requires really quite complex applications to produce coherent, high-resolution models. So we model at a continental and global scale. So simply ramping up these local modeling applications to this scale is simply not feasible for us, both from a computational capacity and the cost and the time it takes to produce that. So we've developed an efficient 2D modeling methodology that accurately represents the physics of water flow across the globe and enables us to model efficiently at these large scales whilst maintaining model fidelity. We've published a number of papers around that, as you can see here on the screen, and I would encourage you to go to our website to access those papers if you're interested. So to produce these models efficiently at scale, we've developed an automated modeling framework, which allows us to model any region globally very quickly, but also importantly in a repeatable manner. When we have new data sets, new terrain data sets, it could be river gauge data, new methodologies, we need to rerun our model very quickly and easily. So that's why we've developed this automated modeling framework. And more recently, we've introduced the ability to model floods under future climate scenarios, which gives us effectively an infinitely flexible model for any recognized emission scenario at any time horizon between now and 2100 at any location across the globe. So we've taken this automated modeling framework that we use to develop our global and our US data sets, and we've deployed it for the rapid assessment of dam failure and essentially the subsequent downstream inundation to determine the impact on the local population and infrastructure. So why is this important? Well, essentially, it's a growing issue. There are a lot of old dams globally. A lot of them have been based on outdated design assumptions, and unfortunately, in quite a few areas, they are poorly maintained. So with those issues of the dam structure itself, we've also got climate change, where we are seeing in some areas extreme precipitation events. And unfortunately, this has been realized in Libya recently with the Mansour Dam failure on the Derna River, which produced extremely catastrophic damage to the city, as you can see here, utter devastation. From a dam that was poorly maintained and that didn't have the right regime in place to maintain it. It's really difficult to comprehend the catastrophic nature of the impact of these types of events. So this is why it's important that we can try and model them and predict them to say, to understand which impacts are going to occur, which communities are going to be impacted, and then putting in disaster risk reduction measures in place to ensure that if these things do happen, we can try and mitigate the impact of them. So how can our modeling framework really help? Well, most traditional model applications require significant amounts of high-resolution input data, which is simply not available in a very short notice period, particularly post-event. By harnessing our modeling framework, which already contains the river channels and defences, we can essentially pour water into that model for anywhere in the world. So we use a simple equation of inflow based on a breach hydrograph derived from known parameters for a dam. It could be the construction, the dam height and width, but importantly, the volume of water it's retaining and the reservoir shape. And we take that hydrograph and plug that into our framework. And this type of modeling is rapid and effective and provides a consistent perspective over a large area of interest with sufficient detail to be valuable for disaster risk reduction planning and, of course, rapid event response, particularly in data poor areas. However, this is not designed to be a very detailed, localized model analysis. This is an ability to have rapid overview and give detailed, balanced indications of the impact of flooding on the population, the infrastructure, particularly for data poor regions. So let's look at the first case study here. The Kakhovka Dam was completed in 1956, and it's the last of a series of dams on the Dnipro river cascade in Ukraine. The dam is essentially a reinforced concrete barrage, and the whole dam is approximately 2 miles long from the edge of the shore to the other shore. And the reservoir behind the dam contains 18 cubic kilometers of water. So that's, putting in the context, that's equivalent to the Great Salt Lake in the US. It provided a number of things: water for the nuclear plant, Zaporizhzhia, as well as the hydroelectric station in Kakhovka itself. And of course, that area is a very rich agricultural area, and it was a prime source of irrigation to a lot of farmers and food production in that very large region. Because of the ongoing conflict in that region, in May 23, they had a lot of, well, prior to May, they had a lot of rain further up the river. Because the dam wasn't maintained as it normally would do, the water levels reached a 30-year high, and a lot of areas upstream of the dam were flooded in areas that hadn't been flooded before. On the 6th of June, an explosion caused significant damage to the central section of the dam in an uncontrolled flow of water cascaded downstream. You can see here, this is an aerial image of the dam a few days before this destruction, and you can see here the level of destruction of the dam and the breaches that were occurred. So you can see that it was a significant impact on the dam. So much so that over 83,000 hectares of land were flooded downstream. A discharge of water immediately at the breach of the dam was predicted to be 30,000 meter cubes per second after the breach, when the average daily output of the dam was 2,600 cubic meters per second. The reservoir upstream from the dam was practically emptied, and one of the implications were there were 28,000 carp that were left there, equating to about 95,000 tons of fish, and this had an estimated commercial value of over $108 million. There were over 1,000 potential sources of pollution across the flood sites downstream from the dam, ranging from water treatment works, petrol stations, landfills, and industrial sites. So it had a huge impact on the local region. As you can see here, we in the early morning of the 6th of June, following the bombing, Fathom were contacted by the UK government under our framework with the Foreign, Commonwealth and Development Office to assess the impact of the event and produce a very rapid report on that impact following the dam's catastrophic failure. By harnessing our automated modeling framework and the fluvial flood methodology, we were able to produce a detailed model and analysis of the inundation over time, which is used by a range of local and regional organizations to support the response to this awful event. And various extracts of the report can be seen here, where we are comparing our modeled output to imagery that was captured immediately post-event. We can zoom in here and look at how the correlation between our modeled extents and the actual flooded extents as well. So it's not only looking at the areas of impact and the depth of inundations we have here in relation to infrastructure, hospitals and roads, but also population, and looking at the density of population that were impacted, particularly in Kherson, but also then in the regions around Kherson, and the percentage of each region of the population that were impacted. So we produced this very quickly and provided that, as I say, to the UK government. So what we have here is essentially an animation of the model we produced, where we have created the inundation model and used the time series here. You can see the hatched areas of the image is the aerial imagery or satellite imagery, remote sensed imagery, that we did a comparison against our data set over time. And as you can see, from the initial event through to sort of 50, 60 hours downstream, we have a very good correlation between the wetted perimeter that was identified from the satellite imagery and the model that we actually developed. So we are pretty confident based on this, a very unfortunate incident, that this methodology works and can give quite a detailed but a rapid assessment of the impact of this type of event. So what I'd like to do now is hand over to my colleague Barney to talk about the Mosul Dam.
Yeah, thanks, Gavin. So turning to a different part of the world that's also been in conflict recently, Iraq. And I've had the pleasure, and I don't say that sarcastically, I've had the pleasure of visiting there about a dozen times on various projects for the US State Department or USAID or partner consulting firms helping deal with the water crisis that country continues to face over there due to floods and droughts, but also water quality and just being able to provide clean water, clean drinking water to the large population there, and enough water for irrigation and deal with all those pollution issues that they have over there. The various pictures in here. There's a town hall meeting on the right-hand side. That bottom left one is a slick of petroleum waste products that's slipping into the river itself. So, but yeah, a whole host of issues over there. I'm going to talk in particular about the northern part of the country around Mosul. Next slide, Gavin. So Mosul Dam, I'm just about everyone's heard of that, I think. Certainly anyone who's listening to this presentation. It's in the real northern part of the country. It's actually right up near the border with Turkey. It's on the Tigris River, and both the Euphrates and the Tigris flow through Iraq, of course, and join together just below, just above where it joins the Arabian Gulf. But the Tigris River is the source of water for Baghdad, and that Mosul Dam impounds a huge amount of water. Next slide. So some statistics on that dam and the impounding reservoir. It's about 370 feet tall. It's about 2.1 miles long in total. It generates a huge amount of electricity, some 1 gigawatt of capacity at the power plant. It's used primarily, though, for water supply, for both public water supply and for irrigation. The land in Iraq is actually fairly fertile, but it's exceptionally hot. So if there's enough water, there's a pretty good agricultural industry that can be supported. It's not very productive at the moment for a number of reasons, but it's not from lack of good soil. The reservoir itself impounds about 2.7 cubic miles of water. It's about 9 million acre feet of water. It's about 4 times the size of Lake Texoma for those who are from Texas or Oklahoma, about 3 times the size of Lake Okeechobee, at least in capacity. So it's pretty big. As I said, it impounds the Tigris River. Most of the watershed, about 90% of it's in Turkey. A small amount of the rest of it's in Syria, and there's just a really small amount of it in Iraq. It's really up there close to the border. And the distance to Baghdad's about 280 miles, and you'll see why that's relevant here in the next few slides. It was built in the early 80s, so it's not a particularly old dam. Next slide. So I've been to Iraq about a dozen times, and mostly in the Baghdad area dealing with issues there, but also up north in Erbil and Mosul, and also down south as well. But when I was up in the Mosul area, I was dealing mainly with a water quality issue that they were having, and there's a big water treatment plant in the upper reaches of the Mosul Reservoir that provides water for the city of Mosul, which is downstream, and also there's a Duhok is a town that's not too far away, but they're having a lot of problem with algae, as I mentioned. But interestingly, when I was there, the plant operators said, "Look, we've got an issue, or at least a concern, with our water intake, and that is that ISIS has been dumping all of their bodies in the river, in the upper reaches of the lake, right near the intake, and we don't know if our water treatment plant is calibrated properly to deal with all those dead bodies." And I chuckled there a little bit, not because it's a funny situation, but just because it's so far-fetched from anything that I'd ever encountered in the US and had to deal with in the US, and didn't have a really good answer for him other than to ask about the chlorine levels. Next slide. So many of you, maybe most of you, may have heard of the Mosul Reservoir because of the concerns with the failure of the dam that occurred when ISIS took control of the facility back in 2014, and they had control of it for several months. But the real issue is that the dam was constructed on a geology that really wasn't very conducive for that type of structure. It's a limestone, gypsum sort of combination of things with large cavities and fractures and things like that. And they, on a pretty continuous basis, are what they call grouting, what engineers call grouting, those holes that are appearing as the underlying geology is dissolving. You can see that in the schematic on the left-hand side, where these fissures or holes or sort of cavities open up as the water kind of flows through it under some amount of pressure. And that picture on the top left-hand side is just a sinkhole that opened up sometime after the dam was built as a result of these fissures and cavities opening up as a result of the dam. And that figure on the right-hand side that you probably can't see very well, but it kind of shows the amount of grout that they're using to fill these holes on a regular basis. And it's of the order 200 tons per month that they're using there. But obviously, when ISIS took over the dam, they were not doing that grouting process, probably didn't have a good understanding of why it was needed, or maybe they did and purposely weren't doing it. I guess we'll never know about that. But the concern at the time is if the dam failed, that there would be as many as 1.5 million people that would die as a result of that failure from the ensuing floods. Like I said, there's a huge amount of water that would move down the valley towards Baghdad and then beyond to the Arabian Gulf. The battle, interestingly, the battle to take over Mosul back away from ISIS again and take control of the dam again, ultimately killed about 9,000 civilians, and that was a sort of a very approximate estimate. So it really was a very big deal for this part of the world. Next slide.
Well, I think we're going to share the
Let's do the video now. So the Fathom folks have put together a video of what that dam break looks like, similar to the video that Gavin showed about Ukraine. So I'm gonna share that video with you. Hopefully you can see that.
Yeah.
And I'm gonna click play on this animation, and what that'll show is the result of a failure of that dam and what that flood wave looks like moving downstream. So the city of Mosul is immediately downstream of the dam, and that would be the city that's impacted first. But Gavin, why don't you talk through the animation?
Yeah, thank you, Barney. So we rapidly developed this in a matter of hours using our existing modeling framework, where we've already got the channels and the defenses built in. And we developed a hydrograph, an ultimate collapse hydrograph, and pulled that into the model. As you can see, this is slightly speeded up, but the flow down the river channels does vary. And here, just north of Baghdad, we can really pick up the detail. Of course, we're hitting the very flat floodplains north of the city. Somewhat slows down the advance, but of course the water finds its own natural channels and also man-made channels along rivers, along roads and other waterways, and you can see very rapidly gets into the city itself somewhere along the lines of a number of effectively a day or two after the initial event. But if you can see, if you look at the bottom image here, you can see where it was zoomed out somewhat. The terrain is really constricting the water and forcing it further down the river itself. So this is not something that's having a localized impact. This has got a significant impact over a very large area. Of course,
Gavin, real quick, sorry to interrupt, but the population of Baghdad is some 8 million people. And as you can see from that floodplain extent, and almost the entire city is inundated. So it's a really big deal. And of course, in this part of the world and other parts of the world, a lot of the population is concentrated to where the water is. So there's lots and lots of smaller villages, larger towns, and small cities along the floodplain of the Tigris River, which is the biggest river through Iraq.
Great, thank you, Barney. So hopefully that gives you a flavor of some of the modeling that we can do. Moving on, excuse me. So that looks at modeling for events where we've got catastrophic failure. What we can do now is look at how we apply our modeling framework to typical applications, particularly in data poor areas. So it allows us to vary the peak flow from the breach, as you can see here, under a number of different scenarios. And based on on the modeling framework, with all the channel bathymetry and everything built in, we can actually calculate with reasonable certainty the impact further downstream for certain communities, and the timing of the impact. We can then overlay population data and get an indication of the number of people impacted in those communities, and we can make certain assumptions around the depth of inundation in certain locations further down the river. So what this allows us to do is produce these types of scenario maps, where we're looking obviously scenario one is a less impact to a really severe event for scenario 6. And it's been able to model this information under a number of different scenarios and been able to manipulate the inputs and the outputs in our modeling framework that allows us to really look at how we can mitigate the impact of these types of events and go more from event response to actually more the disaster risk resilience and planning. And it's providing this data, which is really important, on how we can mitigate the impact of these types of events. This was done in Mozambique, particularly after they had a series of large tropical cyclones coming through. And there was concern, again, from the British government that services may be called upon to respond to that. So we preempted that by going through this modeling exercise. But really, it's a way of giving a very clear representation of how these communities and these types of events unfold over time. And this type of data set can be really easily shared with stakeholders and local communities for that improved disaster risk reduction. So thank you for joining us today on this webinar, and I hope we've been able to give you a flavour of how our automated modelling framework can really be applied to rapidly support disaster risk reduction due to these severe dam failures anywhere in the world, in particular in data poor areas. So to find out more about what we do, please click on the links we've provided here. And if you'd like to find out more about the presentation and the work that AgriStrategies and Fathom have been doing with the Texas Water Development Board, please join us on session H8, which I believe is on Thursday of the conference. So thank you very much for your time, and we look forward to meeting you in person at the event.
Thanks, everyone. Bye now.